Hello everybody, it's Andrew Hutchings here. I am not a licensed physician, never giving medical advice. If it seems like I am, I'm just consolidating medical information, putting it all in one place, along with my opinion. And this video is theory. Sadly, my phone decided to stop recording towards the end of my video and not save it. And personally, I do not like remaking videos because I think it's important for you to see the flow of my thinking. Not that I'm Albert Einstein, but it's important to see how one thing leads to another, and that's how the thinking works. And also, I mean, there wasn't as much of that, but also just my descriptions. There is that, then there's a lot of little things that only when I'm saying it for the first time, and I'm not trying to just repeat something I said, that it's going to come out in a certain way that you'll be able to understand it better. But to get past all that, this video is about receptor down regulation, down expression, endocytosis, destruction, when you have a super physiological amount of something that mimics the natural ligand in an agonist fashion. So basically, you got your natural ligand, which binds to your receptor. And as I said towards the end of my video, it's not like if you have 5 natural ligands and 5 receptors that they're always going to be like they have homing devices, they go straight to them, they stay there forever. No, it doesn't work like that. Everything's just moving around, and based on its electronic properties, where it has more electron density in it, it makes it pull in certain ways, and that changes the way it moves. And that makes it more likely so that if it bumps into something, maybe it's going to interact the electronics, like high electron density with the low electron density, and that's going to be kind of like magnets, pulling them together. Maybe that will pull some other part of it. That will latch on, maybe it'll change the shape of it. But basically, it's all the electronics. But the key takeaway thing from that is that everything just bounces around randomly, very fast. Even the molecules themselves. Say there was a molecule that was drawn like my hand on the stick drawings. It's not actually like that. It's like, that's what it's actually doing. And sometimes you even have the actual atoms switching with each other at ultra speeds. Nothing is static. That's a key thing to know about molecules. So back to the original topic of this video, and I'm going to use opioids as an example of it because it's easy. This also applies in a slightly different way to spike protein binding to ACE2, but it gets endocytosed for a different reason, but it's very possible that it's related to the natural reason why it would endocytosis. Can't say 100% sure, but that's why I'm going to stick with opioids, because they're more well-known, been around longer than this new thing I won't say the name of in case it's going to get my video have problems. But okay, so you have your receptors, you got your natural ligands, you got a little bit of natural ligands, and you got a decent amount of receptors. That way it's bouncing around, it's going to land on one of them, it's going to come off, it's going to bind to another one, it's going to come off, bind to another one. Now if there were, instead of 10 receptors all around this bouncing around ligand, if there was only one, it's much less likely that this ligand is going to bump into it, come off, instead of bumping into another one, bumping into another one, bumping into another one, and so on. It's going to really cut down how much interaction there is. And if you're introducing extremely super physiological amounts of an agonist that mimics the natural ligand, because that's what an agonist does, unless it is the natural ligand, in which case it doesn't mimic it. But when you, instead of having like 5 ligands, we'll say, you got 5,000 synthetic analogs that agonize the receptor, and very possibly even to a higher degree than the natural one. So now all those receptors that normally are only bound some little fraction of the time, but a decent fraction of the time, they are just 100% full almost 100% of the time. And they are getting extremely strong signals, and the body's going, this isn't right. People say, oh, the human body's never in homeostasis, blah, blah, blah. But the body wants balance. Whether you're going to be a stickler for calling it homeostasis, I do personally. Even like, oh, you're only in homeostasis when you're dead. Sort of. But yeah, you introduce that massive amount of synthetic ligand mimicking thing that gives an even stronger signal, and the body freaks out. So what does it do? Well, there's multiple things it can do. It can literally just have some proteins go onto the receptor. They tag it, you could say. I mean, that is what we say in scientific stuff, but I'm trying to just say whatever is best for you. So you get this tag put on it, and it triggers it for something else to eat it. Or perhaps it's on a cell surface, and it gets pulled inside of the cell. Or perhaps it goes into some other vesicle of some sort. And then there's also your DNA, which gets read to RNA, which then gets read to the proteins. Receptors are proteins. You're also going to get your body telling it's not that anything tells each other, it's just that all these things have mechanisms of feedback. So the DNA is going to be making less RNA, and the RNA is going to be so you already have less RNA to make less protein, but on top of that, there's going to be other changes, because when RNA binds protein, it doesn't just read it out perfectly, make a zillion copies, and that's that. It needs other things to bind that allow it to read out 1,000 or 200 or however many. DNA does similar stuff. Everything has complications, but on so many levels, the body is making sure that you get less receptors. So if you were like an opiate addict for a long time, especially using something really strong like fentanyl, which is an ultra strong agonist, way, way, way stronger than your natural one, and if you're always having sky-high levels of that in your blood, so every single receptor in your body is always being bombarded by it, your body's going to be decreasing the amount of receptors as much as possible. This is why tolerance sets in. Remember, a friend of mine was like, I made another video on this, is tolerance real? You can search it, but I explained it in this video also. He was like, no, you don't get tolerance to drugs. If there's the receptor there and it binds to it, it's always going to work. And I was like, no, it's not always there. And I told him about all this stuff I just said. So the issue is, say you had been using super large amounts of something that binds to it and agonizes it super strongly, and now your body has very few receptors. When you stop taking that, now you have your little tiny natural amount of natural ligand. And when there's not very many receptors, it's kind of just bouncing around most of the time, not binding to anything. Occasionally it binds to a receptor, gives it a little activation. Occasionally it binds again, versus bound the second it comes off, another one binds to it and with stronger agonism. So the issue is that when you don't have very much binding of your natural ligand to the receptors, because the receptors are almost all gone, your body is going to be way out of balance. Like in the case of opioids, your sympathetic nervous system is going to be going haywire. Your body's going to ache. Opioids dysregulate parts of the brain that control like body temperature regulation. So you're going to be all over the place body temperature wise, but in general cold, because opioids make you feel warmer. It falls under something I already said, the sympathetic super excitation. That's going to be like high heart rate, vasoconstriction, dilated pupils. Intestines are going to be hypermotile, hypermobile, motile. Both words are used. I've always said hypermobile. I'm not sure. I'm pretty sure I've always said hypermobility and hypomobility when referring to the intestines. But you could say hypermotility. Not that that's important. So now getting to some other theory. So say you're at that situation. You have very few receptors, very little natural ligand. Not a good situation. It's going to take a long time for your body. I mean, not a long, it depends on everyone's body. And the body is always trying to get back to baseline, so it's going to take some time for that to happen. But is there a way we could possibly speed it up? The answer is most likely yes, because the body has feedback mechanisms for everything. So if you do the opposite and use a super potent antagonist of that receptor, the issue in this case is that the one that is available has an extremely short half-life. Not extremely short, but like pretty short. And it would cost you a lot of money if you wanted to actually go, but I'll just say what it is. So naloxone, Narcan, it's given to counteract opioid overdose, whether it's a hospital setting, an ambulatory setting. Technically that doesn't mean the same thing as inside an ambulance. So I'll include inside an ambulance setting. Could be your friend giving it to you, could be your mother, whoever. But Narcan, as I'll refer to naloxone because that's a pretty common name, it is an opioid antagonist. The issue is it doesn't last very long, like 20-30 minutes. I think maybe a little longer. I mean, main strong action is probably going to be like 20-30 minutes. Again, I didn't brush it up on any of this before. I don't do that with any of my videos. I'm lazy. I know this stuff. I don't need to be exactly 100% precise about everything. You can look it up and find the exact half-life on Wikipedia if you want. But the half-life doesn't mean the same thing as how long it's going to have its main action. Something can have a, let's just say, an 8-hour half-life, but the main action is actually going to be for, like the peak action is going to be for like an hour, main action like 4 hours. Of course, this differs with everything, so your body deals with everything differently. General rule of thumb is cut the half-life in half, and that's going to be the main-ish action, and cut the half-life in like an eighth, and that's going to be your peak effects. So if you had if you could do like an IV infusion of naloxone, which would make you feel not very good if you were dependent on opioids, but if you could do that for a prolonged amount of time, and I'm not a medical doctor, licensed physician, I'm not recommending this, I'm not prescribing this, but you would be binding to your receptors, giving them negative signals, and your body would be going, what's going on? Why am I not getting any positive signals from my opioid receptors? And it would upregulate them, doing the opposite of before. If some of them were endocytosed, perhaps they come back to the surface. The ones that were destroyed, they just have to be remade. So the DNA goes to the RNA, RNA makes the proteins, receptors are proteins, and you end up with more of them so that your little tiny bit of natural ligand has a lot more of them to bind to, and you're back more to a normal state. Now, the only thing is that I should say about this, if someone were to attempt it for opioid shortening of withdrawal, is especially if you're going through heavy withdrawal. Well, I mean, especially if you have heavy use, because you don't need to stop using to do this. You could, I mean, it's going to make you feel horrible, but say you're using fentanyl every day. If, in theory, you could hook yourself up to a naloxone IV, give yourself 4 milligrams per 30 minutes. Every 30 minutes, like 8 milligrams per an hour IV infusion. I mean, it could take more because fentanyl is serious stuff. Got a lot of fentanyl molecules. I mean, this is just a like average. Now, it could take less if you're just using a little tiny bit of Vicodin. But yes, if you were to hook yourself up to that naloxone IV, you would instantly go through withdrawal, because all of a sudden, instead of having all those agonists that agonize even stronger and they're at super physiological levels, now you've got super physiological levels of something that's not supposed to really even be there. I mean, I'm sure the body has some minute quantities of opioid antagonists, but you've got these the synthetic ligands, the Narcan, that bind to the receptor really strong, but instead of activating it, they send a negative signal. So you go from all those like fentanyl molecules always being bound to the receptors, they're getting the max positive signal they could possibly be getting, and all of a sudden now you're getting the max negative signal you could be getting. Not going to feel good, but that's going to start the body into upregulating its production of more receptors and bringing more back, if it can. Hope you like this video. You can hire me for training, advice, consultations, plans, whatever. I know I'm not in the best shape right now. I'm busy with other stuff. You can hire me to tutor you in chemistry, biology, chemical biology, making viruses, making vaccines, whatever you want, but not bad viruses, because that wouldn't be nice. Yeah, whatever you want to hire me for, I would greatly appreciate it, because don't even want to say it, but because I've got like no money. So yeah, that's why. And I'll make sure you get good bang for your buck. You will get results. Oh yeah, and the service that I really like personally is gathering medical information for people and rewriting it or talking about it, or however you want to do it. I mean, I find talking is the best, but it can be helpful to have something you can look at again. But in a way that you can understand it to make the best, most well-informed decisions about your own health, rather than just blindly rely on somebody else. Like, they said it sounds good. I mean, I guess you could say the same thing about me, that I could just say stuff and it sounds good, but it's not really true. But I'll back it up with scientific studies, and I know other people could do that also, except I am a very, I don't know what to call it, analytical person, where I realize the faults in the studies. You can't just read a scientific study, go to their conclusion, oh yeah, that proves everything. No, there's often a lot of errors in their studies. So you only can use certain information. You may not be able to use their final conclusion, because it might, I mean, if something else doesn't have the same errors, gets the same conclusion, great. But if you only got like one study, bad methodology, or you even got a few studies, but the methodology is bad, it's like, you know, maybe it's gonna do that, but probably not if we change this up. And another thing is, and it's sad, especially in the scientific field, people overlook how different every single human body is. And I think part of this may be because when they work in labs, they use genetically identical cells. And when they use living beings, like rats or mice, they use genetically identical mice. Now, they may have two different breeds of genetically identical mice. This one's genetically identical to all his bros. This one's genetically identical to all his bros or twins, whatever you want to call them. So you get very steady numbers, when if you just picked a whole bunch of random people